Hello everyone. Today I am going to talk about our work modeling label correlations with latent context for multi-label recognition. In the literature, previous methods focused on capturing label correlations to improve the performance of multi-label image recognition. Although those previous methods achieved the considerable improvements, however, we argue that the label co-occurrence may be insufficient to represent label correlations. And the label correlations can be constructed through reasonable use of the latent context information. For instance, the labels of person and surfboard frequently appear together. Conventional methods consider such labels have a direct correlation and directly model the correlation between labels. However, multi-label images could be human-centered, and the label person could frequently co-occur with other labels. Inferring other labels with person cannot lead to accurate results due to the high co-occurrence frequency. Based on the above analysis, we propose that the correlation between labels depends on the latent context information. Therefore, we consider that embedding the latent context information into label features can bring the potential for directly modeling label correlations from an input image. In this paper, differing from the traditional label correlation assumption, we propose a novel latent context information embedding framework for multi-label image recognition. Our framework contains 3 modules: the multi-level context feature fusion module, the latent context information embedding module, and the label correlation capturing module. Firstly, it is difficult to define the specific context information, since we assume that latent context information appears in various forms, such as scene, background, pose, texture, and color. These high-level and low-level latent context information are contained in different levels of features, and all kinds of context information may influence the label correlation modeling. Therefore, to obtain sufficient latent context information, we design a multi-level context feature fusion module, which fuses the features from different network levels to extract the context information from low-level to high-level. Then, we design a latent context information embedding module based on the multi-head cross-attention mechanism. It can embed the latent context information into label features to bring the potential for directly modeling label correlations from an input image. Finally, the label correlation capturing module is designed to capture the label directly correlation in full label and partial label manners. For full label, we utilize self-attention mechanism to capture the label correlations. For partial label, we use inference tokens to randomly replace one of the label features, and use inference tokens to predict the replaced categories. We conduct extensive experiments on generic multi-label image recognition and partial label multi-label classification. For generic multi-label image recognition task, our method outperforms previous methods on both MS-COCO and NUS-wide datasets. We also conduct ablation studies to verify the effectiveness of each module involved in our framework. Table 3 shows the performance by progressively integrating the above 5 modules. Solely applying MLFF on the backbone gives a 1.8% map improvement. This result verifies that the low-level information is complementary to the high-level information since it can enrich the latent context information. Then, the context-aware categorical features, which can be directly utilized to predict the final result, bring another 2.3% map. This result suggests that the latent context information can make labels have a direct correlation and effectively improve accuracy. Subsequently, leveraging the transformer encoder to capture the correlations with full labels improves by 0.8%. Due to a lack of spatial information, we attempt to fuse the spatial features into categorical features and obtain 84.7% map. It is worth noting that we also directly utilize the spatial features to model the co-occurrence, and it only achieves 82.7% map. This result verifies our motivation, i.e., there may not be had a direct correlation between these labels. Finally, capturing the label correlation with the partial label can achieve 86.8% map. We also visualize the learned context-aware categorical features to show if these features contain direct correlations. We can see that after embedding the latent context information with our method, the context-aware categorical features maintain meaningful semantic topology. For partial label, our method obviously outperforms the previous methods, which demonstrates the effectiveness of our method in the partial label scenario. Besides, compared with the baseline method, we observe that as the proportion becomes larger, the improvement of our method is more significant. Thanks for your attention.